Morning, guys, and it's George investigating. Isn't it funny or ironic that they keep looking at this number 10? Out of all this whole structure, that they bite on the number 10, that they do something with this number 10. Let's go ahead and jump in. This, of course, is my model you're looking at, the larger model. Okay, so today's video, let's just go over a couple topics, a couple little small points. That's the larger, this is the larger number 10, 11 scaled to 10, 11, just scaled up. This does not have any weld on the base of it, so there's no weld down there. Let me change the ISO a little bit here, guys. Oh, wrong way, wrong one rather. There we go. Now we can see a little bit better. There's no weld on it. So no matter what force I apply at the top of the joint of the nodal area of 10, 11, the top here, and no matter what downward force I apply, it is not causing this to shear. It would buckle, twist, and deform before it's sheared. That little bit of a rod that I have in there, the back of it, that rod, as you can see, I painted in white, the white line there. The back of it is, slide it a little bit for you. Good. That's indicating roughly where it is, but at this point it's right, it's at the base of the back of this metal, inverted inside of it. So if you can imagine, it can't slide through there. The whole slide action is being resisted at the base here and the connect of these two together, the top one and the lower deck and number 11. That for it to shear, this one's not moving. It is moving a little bit if you think about it, sagging down. But this one is moving outwards if you apply the load to it under their shear friction, under shear friction, right? Under friction, under the incline, load on an incline, slide. It's approximately 32 degrees, meaning a flat, right? 32 degrees, so 32, 34, 35. It's all over the place with where I've got numbers from. The way they tested it with Denny Pate's forensic analysis engineers, the whole team of PhDs or whatever they are, they used two of these together and just decided that's how they can create. They just used the opposite side of this to see if they can create a slide. But of course it wasn't also at 32 degrees, because 32 degrees and 32 degrees does not meet a flat plane. And you see in the images that their model meets in a flat plane. So now here are the experts, engineers, forensic engineers that are trying to show that shear plane is the issue. This is the same hocus pocus stuff that Denny Pate in that meeting had, that nobody stood up. I have not seen one other engineer, save one, that has shown this to be, extrapolation is to be off base. These angles do not equal the shear plane as it presents. 32 degrees, the opposite of if they were going to do this, would be what? It would have to meet at 158 degrees. It was 32 degrees, but they've got this at 45, meeting at a 45. So they're shear planing. They're shearing the material at a different rate. Also, they don't have the cracks represented in their model. There are tons of cracks in the real world. It's not represented in this model. They also don't have the upright present that would have been resistant force. They don't have the post-tensioning bar that would be the resistant force. So their model is worth jack shit. So they used 45s. So that's an odd duck, right? Let's say they did use 32 and they flipped it over and did that. Well, it's not meeting, it's meeting a 90 degree abutment also. The abutment is the other bar inside here. It has a resistant force. The plate back here is also resisting. So they have these resistive forces that they remove in their imagery to allow this to slide off. But better than that, they allow it to slide off from an imaginary force, I call it, because this has no force on it right now. I mean, you know, it's I'm not going to argue micro forces, right? But there's no force on this right now. In other words, I'm not going to argue about the weight of it and all that. Just the top of this nodal area has nothing going on. There's nothing pushing it down. Now let's add the canopy on it. Well, the canopy is a dead load, so the canopy would be a force here and out to number. So back to the model now. So the canopy would be the force we're talking about from here to here. Some force is going downwards. Nobody's talking about it going upwards. So in their theory, it's all counterforce. This would be like trying to go through a football player, right? It exists. It does exist as a dead weight, interfering with number 11 from pushing it off. But they have number 11 being a push off 12, and 12 is a pushover. 12 means nothing to it. Me, I do kind of have it as a pushover, but their theory is slide friction was lost here, and it did the push out. But this can't elongate by itself. As we look at it, no matter how much we all focus on saying now, elongate, push it out, it just can't do it. Let me just make sure this is cut free. Make sure it's broken free, and then we'll watch it. So let me do that. All right, so I bent it up. And as we visually look at it, use our brain, we all focus. Nothing. It's not sliding outwards. If I were to put a load here now that's not there, what would happen? Well, it's going to put this under a lot of stress. The load being here, it's going to want to cause it to sag, right? Let's look at that. So I bent it up. If I put a load here now, this is now going to want to be in tension to try to stop this from happening. In tension. This one in tension. This is nothing. This will be nothing but a dead weight helping it come down. Oh, I got to go feed my cat. Just pulled up. Hold on. I'll get back to you. So let's get back to this. So this puts this one in tension. Once you remove this out, as the load if the load the deck deflecting, and since it's a span, and I remove this out, and I remove the post tension bars, which I'll put back. The deck deflecting. That's Bruce. Bruce is looking for his brother or something. Bruce was a stray that I just bought inside one day, and he's quite happy to be here. So without the post tension bars, which they're detensioned on the 10th, right, the day of the move, this looks like, with the cracks presented, it looks like this to me. Those cracks to me are open, but we have to put this back in to keep the 12 encompassed on the deck still. So right now, if I do this, I'll put it back, you'll see what the effects are. Let me do this first. So right now, we get deflection. Look at this. I remove the bars. Remember, this is the same system we've always had. If I do this, we get deflection in the system. Where are we getting the action at? The reaction? Oh, great. Let me go ahead and do this now. Bruce is coming over, guys, so you gotta bear with him. I'm in George. That's George. He's playing along. I won't climb up on the structure now, but I'm showing you where the reaction is happening now. Once you remove the detention, I pull that out of the way to show you that I'm saying it's not in compression, that it's not existing. When I load this center area here with the dead load, you're going to see the reaction is what we see in the brakes. Because the span now, this is no longer working together. This is no longer working. It's number 9 to the deck, as I stated, and from here to here going downwards. This is under tension and compression, depending on where how the forces are. Here we go. You see the reaction right there? Right there. I'll do it again. I'm out here, and you observe the reaction. So that's why I'm stating number 10 is not in compression, as everyone keeps showing or trying to talk about. Let's see if I can get a little better lighting for you again. And do that. Now you can watch that hairline shaded area, if you will, right here. Let's do that again. Oh, okay. You know what? Let's do this. Let's put this on the bridge. Good. That's our indicator. Watch as I load this. Watch as I load the bridge. Our deflection is thereupon there. I slide it back towards the center of the bridge a bit. I do the same deflection, and you see it's not opening up. Now let's slide it back to the point of our failure again. And I press down the center of the bridge. You see the spacing. Explaining why the bridge broke here and here, which no one ever did. NTSB report never explains why it breaks here and here, the decking. They just talk about some silly ass crack column. I call it a column, right? Because that's the way I look at it. I look at these things as loads on them, and I visualize not just as a truss. Of course, we're talking about a truss system, and this would be a truss in that system, if you will. But I visualize them as columns and what each column / truss is doing. It's the way I visualize. Sorry, guys. You can join in on that visualization, help you understand it better, or don't. Again, zoom in, take note of our indicator. I'll put a load in the center, and you see the gap created. This could only take so much. Now, if once I put this post-tension rod into the system for you guys, maybe tomorrow's video, Christmas, and I tighten that up so taut, it will become redundant if I do this tight enough. I haven't done it yet, just so you know. It can become redundant enough where it won't allow deflection. Because I want you to take note of the reaction of the base. Now the base wasn't tied down either, so all this stuff stacks up against this system. If this base was strapped down, tied down, that would also help it keep it redundant. If it was locked into the pier, this base would not also be able to take the same reaction that's needed for this failure. Watch the base. See the kick out, how it rides on the heel, if you will, over here. That's the same thing on the other end, but this more so has an issue this end because number 11. We talk about a couple of things that this does have some redundancy in it. You see when I put back number 11 where it's not, if it could hold, which NTSB, Danny Pate, everybody's saying, and all the engineers and all these other groups are saying that that 11 is contributing. If I put 11 back as a contributing factor back into the game, I will not be able to get this deflection here because the structure is showing redundancy, in my opinion, with the web system. Once you lock it back in. Okay, so I friction fitted it. The bar's not in there. I'm going to put the same load on again. Wait a minute, let's put this on. I'm going to put the same center load on again. And this one's giving you halo, right? Too much? And we're going to watch it now, how this will not deflect. I'm on it again now. See that? Now, I want you to watch that as I climb up with bare feet. And I'm going to load it. Yeah, I can actually hurt myself pretty good this time, but I'm sure that what I'm theoretically telling you is true. So I'm on it now with bare feet. This is showing you that I'm telling you number 11 is not contributing. It's not part of that system. Oh, let's do that again. Let's so nobody thinks I'm pulling a magic trick. Let's do this. Now, if I were to remove 11 now, we get the issue. This is why I keep telling you 11 is not in compression. It's failed its intention. It's not contributing. It may look like it in all the engineers' minds, but they just don't have the right mind. I mean, hopefully this will be my video that sells everybody. That's what it looks like connected. No deflection. I then detension, keeping it live. Sorry, I won't be able to edit this video. People will think I did a magic act. So I'll have to keep my stumps Now we detension it. Put the load there. No way am I walking on there now. And we get deflection. End of this video. Hopefully you guys will enjoy this one. So again, that's intention. It's not, there is no, you know, I'm frustrating myself now. There is no, that connection has failed. It doesn't exist in this failure. That gets us a failure here and here. That the loads are from this deck are resolving itself from 9, 10 out to here. Sure, as it deflects, some of this is intention pulling down, holding onto the canopy still, and well, hell, you see what's going on when you remove number 11. Now, the deal is though, that I'll do in a video as I stated, the post-tensioning in the deck could have been the redundant factor. It could have saved this, because I'll do again, like I said, I'll do it tomorrow, maybe later, and I'll post-tension that up. We'll do it with this, like this, and theoretically, I should not, the deck should not deflect. Now, let's talk about the steel in my model. The defects of using this model is that the steel is already acting continuously as a reinforced bar. Because it's steel, all of it's steel, exactly what I want, but I'm going to confine it more with some more post-tensioning. But the concrete wouldn't react the same as this. The concrete would be brittle, and would have, in this test model, if I made it out of concrete, we'd have broken concrete, and I wouldn't be able to do the multiple series of showing you the videos. I'd have to have multiple of these, because I'd be breaking them up left and right. There'd be cracks everywhere. That's why the steel works for me. The proportions work for me. The theoretical model works for me. Hopefully it works for you too. End this video with that.